Okay, so here again, we want to determine whether the series is absolutely convergent, conditionally convergent, or divergent. And here's your given series this time. Let me box out the question here. So you always start with by checking for absolute convergence. So we start by considering the series absolute value of all of this. If you take the absolute value of all that, then this is going to turn into just 1 when you take the absolute value of your negative 1 to the n. This is positive for every value of n from 1 to infinity. This is always going to give you a positive number. And so when we check for absolute convergence in this example, take the absolute value. I want to not trying to avoid writing this whole thing out. And you'll get this. So just n plus the square root of n over n cubed plus 2n squared minus 2. Okay, so we want to determine whether this series converges or diverges. So if you consider all your options, when you have something messy like this, then my go-to test in this situation is limit comparison test, where I compare it to the series where I take just the dominating term in the numerator, dominating term in the denominator, when I'm looking at a mess like this. So the dominating term in the numerator is going to be the n, right? As n approaches infinity, this n is going to get much, much bigger than square root of n. Over dominating term in the denominator, it's just highest power, so n cubed. Okay. And so that reduces to 1 over n squared. So that's why limit comparison tests take the dominating terms, and it usually simplifies to a nice simple series. In this case, a p series with p greater than 1, so I know that this converges. Okay. So now I need to work on this limit. So the limit as n approaches infinity of our given series, so n plus the square root of n over n cubed plus 2n squared minus 2 over 1 over n squared. But if it's okay with you guys, instead of writing over 1 over n squared, or maybe I will write it, I'll put it in green because that's kind of faint. Over 1 over n squared, I'm going to go ahead and bring that up and flip it over. So I'm going to go ahead and swing this up here, n squared times n squared over 1, right? Instead of dividing by the terms in the other series. Okay, so that, what do we have then? Limit as n approaches infinity. This is probably going to be in my way. So n squared times this will be n cubed plus, if this is n to the 1/2, times n squared, so that's 4 over 2. So n to the 1 over 2 times n to the 4 over 2 gives me n to the 5 over 2 here, over n cubed plus 2n squared minus 2. So if you've gotten real used to using that theorem that says for a rational function, which this really isn't a rational function technically when you've got a fraction in the exponent like that. But for a rational function, we take the ratio of the leading coefficient, so in this case 1 over 1. Turns out, yeah, this limit will be 1, but technically we're not supposed to use that theorem about leading coefficients since this is not technically a rational function. So just to formally show that this limit is 1, we could use L'Hopital's rule. So this limit has the form infinity over infinity. I can apply L'Hopital's rule. So this is equal to the limit as n approaches infinity of 3n squared plus 5/2 n to the 3/2. Sorry for the TV in the background there. Okay. 3n squared plus 4n, derivative of that 2 will be 0. Okay, so still technically not a rational function, still has the form infinity over infinity, so I could apply L'Hopital's rule again. Might have to do it a couple of times actually. Let's see, what's going to happen now? 6n to the first. If the 3/2 come down, 3/2 times 5/2 will give me 15 over 4. N to the 1/2 over 6n plus 4. Still technically infinity over infinity, unfortunately. Okay, and I don't have a great spot to write it. I guess I'm going to come up here. So now that's equal to, if we do L'Hopital's rule again, the derivative would be 6 plus, if the 1/2 comes down, that'll be 15 times 1 over 4 times 2 into the negative 1/2, all over 6, right? Okay, and so that's limit as n approaches infinity of 6 plus 15 over 8 into the negative 1/2. So that's a square root of n down here, all over 6. Okay, it's almost over because I know it's gone on forever. As n approaches infinity, this is a number over infinity. That's approaching 0. And so we've got 6 over 6. So there you go. The limit's 1. And so we kind of could have applied that rule about leading coefficients to begin with. But I just wanted to work it out to show you it's okay. We're going to get that same result. Okay, so the limit's a finite number, which means the series behaved the same way. So we go back and look at what we're comparing it to. We compared it this time to a convergent p-series, which means the series we're comparing to also converges. So this series converges. Okay, this series converges, which means that this original series up here is absolutely convergent. So in this case, our answer is absolutely convergent.